All right, let's get started. We have stuff that we're going to introduce today, but we won't focus on it today. Like the curvature and tangent circle, we'll talk a little bit more about that next time. But I do want to get to the FernAFrame, which is something that I was starting to introduce last time. And the FernAFrame includes 3 vectors. The idea behind a FernAFrame is that if you're, yes?
Sorry, I've noticed that you haven't been putting up the notes.
Oh, yeah, if you don't see the notes, so the notes, usually I try to put that up the day of, and if you don't see it there, you can send me an email. The videos take a little bit longer, maybe a day or two. Yeah. So if you don't see it, send me an email so I'll know.
Yeah, so you're still recording?
Yeah, I'm recording it. I just haven't put it up. And so also if I don't hear from anybody, I just assume that nobody looks at it anyway. So yeah, if you don't see it. Yeah, I think so. Danny?
Yeah, then I was not here last Thursday. Did you ever get those up? I haven't checked. I checked like 2 days ago.
I'm not sure. Maybe the video's not up.
Yeah, the video. I don't think the notes are either.
Oh, really? Okay, so I'll make sure that those go up tonight.
Thank you so much.
So I'll try to get at least the notes up, and then I'll see how long the videos take.
Definitely. Thank you so much.
But I do want to talk about the FernAFrame today in detail, and that is the idea is that if you have a curve in space, and the curve can visualize how the curve looks like. Maybe I should have drawn this in black. I'll draw it in black. There you go. Yeah. But the idea is that if you pick any point on this graph, on this space curve, you can. I think the analogy that I gave last time is that you can pretend that you're on a roller coaster, and as you're in a roller coaster, you're twisting and turning, you're going upside down and all that stuff, and so you have some sort of orientation. You're in a roller coaster, you're looking at the world from your point of view, and so from your point of view, you can see the ground, you can see some birds flying, you can see other rides or wherever you are, but you can see that from where you're looking. And from where you're looking, it would be nice to determine what it means to go straight ahead. And based on your roller coaster, that would be the tangent vector. And it turns out that all you're really caring about at the moment is the direction. You don't care about how fast you're going. I mean, you could probably feel how fast you're going, but the speed, remember, is the magnitude of the velocity vector, but you don't care about that, so we're just establishing some sort of a frame. And then there's an acceleration pull somewhere on this roller coaster. So the acceleration pulls you a certain way. I'll draw the acceleration in I don't know, in black. But in terms of creating a frame, you don't necessarily want to go in the direction of the acceleration as your second vector. And so, the IJK vectors are unit vectors, and they're all perpendicular to each other. And so it would be nice to create a frame that's perpendicular to each other here as well. And so there's a second vector that we're going to talk about that should be perpendicular to the tangent vector. And here's the tricky part, is that vector should be in the same plane as the acceleration vector. Okay, so that idea is not that big of a deal, but I think it is important to be able to state. So we have the unit tangent vector, which we'll call T, capital T, And now we've just discussed another vector that's perpendicular to the unit tangent vector, and we'll call that the unit normal vector, n. And then to complete this three-dimensional frame, we need another vector that's perpendicular to both of these two vectors, and it will be called B, the TNB, right? So, and it has to be perpendicular to these two vectors, and actually, you remember how to get, if you have two vectors, you know how to get a vector that's perpendicular to those two vectors? You cross them. So if you cross T and N, you get a third vector called B, and B stands for the unit binormal.
If you had N and B, could you cross them to find T?
You can, yeah, but you're most likely going to find T first.
Okay. Or I guess I meant to say that if you have two of the three, you could cross to find the third.
Yeah. So these are all perpendicular to each other, not counting that extra acceleration vector that I drew. But the idea is that at every single point on this curve, you will have your own frame. So you're in a roller coaster, and then you time yourself at t is equal to 0, you have your frame of your reference, and then you move somewhere else, you have a new frame of reference, and then you go down, move somewhere else, you have another frame of reference. So think about those video games where you're looking at a frame of reference of your surrounding, and somebody else is playing in some three-dimensional video game where they're looking at their frame of reference. And so they have their own FernAFrame as they're walking around in this environment trying to kill people. Or whatever game you're playing. Score goals or... So that's the idea. So what we want to do is we want to build these. And so I'm just going to present some formulas for you. And this discussion is actually amidst all this information about the curvature and arc length and stuff. And so we'll briefly introduce those. We'll talk more about the arc length and curvature tomorrow. But for now, let's focus on trying to find our FernAFrame. So let's go through an order here. The arc length. We saw an arc length formula for 2 dimensions. The arc length formula for 3 dimensions is simply throwing in that third component. And what that boils down to is that this arc length formula can be rewritten in a nice and simpler form where you're taking the magnitude of the derivative. So essentially, you're taking the magnitude of the velocity vector. So to find out an arc length, so imagine, let's keep this roller coaster analogy. Imagine you're on the roller coaster and you're building your FernAFrame in a roller coaster. But if you want to figure out the length of the track in the roller coaster, you would just find the whole track and integrate it. Find the magnitude. If you can describe your track as a vector valued function like this, you just find the magnitude of the velocity vector and then come out with a track. So this gives the arc length formula. Now there's this idea of integrating with respect to arc length that we won't talk much about. So maybe we'll dive into it next time, but we won't talk about it. But it is important in building some of the theory behind the curvature. So I'll just put this in our notes to say that this is just going to go in our notes. So I don't know if you remember, but when we were parameterizing, you know those lines that we were finding, and you want to find an equation of a line passing through 2 points, and then what you need for an equation of a line is a point and a direction, so you can, between 2 points, you can have 2 different directions to go, and between the 2 points, you can use either of those 2 points. So there's many ways to express a parameterized curve. And so because there's many ways to express a parameterized curve, what we could do is we can think about, theoretically, think about a way to express a parameterized curve so that it's called parameterizing by arc length. So when you parameterize by arc length, you simply parameterize it so that the length from some value to some t value is going to be exactly the length of the curve. For this idea, like I said, I don't want to dive into it too much. For this idea, let's take a look at the circle. That's the circle. R of t is equal to cosine t. And just for the simplicity's sake, let's stay in 2 dimensions. Oh, my Z doesn't work again. So let me put another different parameterization here. Let's call it R2 of t cosine 2t. I'm going to call it cosine 2 pi t sine 2 pi t. So both of these, if you were to graph this in some graphing program or even in your calculators, you'll see that this thing will both draw the circle. So they both draw the circle. They both parameterize the same thing. So if we want to find the arc length of a circle, we can use either of these formulas. But if you look at that first one that we got, this first one is actually one that can be said that you're parameterizing by arc length. Because the idea here is that if you integrate from 0 to t of the magnitude of this thing, the magnitude is 1. Sine squared, cosine squared. So the magnitude is 1. du, if I'm looking at this formula, then this is going to measure the length of the curve by exactly what that length is. I mean, this t value over here will kind of dictate the length of the curve. All right? Just think about that and put it aside. There's this idea of parameterizing by arc length. You can read through it. We're not going to dwell on it too much. So, if you want to dive into this a little bit more and want to find out more about it, then take a look at these 2 examples and do some integrals. Otherwise, don't worry about it. Yes, it's knowing the function before putting into the integral. So you're kind of essentially knowing the answer already, and that's the idea. And so that idea is really just for theoretical purposes in establishing ideas like the curvature. So this is a recall. Oh man, that means I don't have the other ones. Oh, there it goes. So let me just put down the T, the N, and the B definitions. I'm going to take a few more things over here. So the FernAFrame is based on 3 perpendicular unit vectors. The unit tangent. And this one we introduced already, and I think this is fairly straightforward. It's a tangent vector, but you want to make it a unit length. And so you find the tangent vector and divide by its magnitude, and then its unit length. The unit normal this idea is a little bit trickier, and the idea behind this is that if you take the derivative of the unit tangent, you're going to get something that's going to be perpendicular to itself. Now, the thing about taking this derivative is when you take that derivative of this unit tangent vector, it may not be of unit length anymore. And so just to ensure that it's unit length, then you want to take the divide it by its magnitude. So this, I think, is the trickiest one. And then the last one is easy because you're just crossing the other previous 2 vectors that you found. So this is your unit binormal. So doing this in general is really difficult calculus. It's not difficult, but it's more like tedious calculus. You're taking derivatives of things, and you're taking derivatives of square roots. So the derivative of t will include, taking the derivative of this fraction, which you can think of as a product. And it can get really complicated because you might have some square roots involved. So in general, it's not a very nice thing to do by hand. But I'm going to have you guys do it by hand. And what I'm going to do is I'm going to use a computer to show you how this thing might look like. No. So let's come up with some weird function. I don't know if weird is the good way to... Oh, let's not. Why don't you just do it? Before you do it, I want to show you a picture of some stuff. P-U-T. So what I did here is, remember this curve, cosine, sine, and then I have another cosine or sine function for the z component that's that changed the frequency, so it's sooner. So it's like that wiggly thing. So that would essentially describe your roller coaster. And what I have here is I have a Mathematica program animation that takes a look at your tangent vector as you move along that roller coaster. All right, and it's a unit length, so the length isn't changing. So it's always a unit length. Okay? So that's a tangent vector. Now, let's add on the normal vector. Now, the normal vector is perpendicular to the tangent vector, and it's kind of going in the direction or in the same plane as the acceleration vector. So as you move along, you'll see it does a little twisting and turning. So imagine yourself in a roller coaster, and the red vector is the vector that tells you the direction you're going, and then the green vector would be your like left side of your body where it's pointing. Okay? Yeah? The green arrow is your left hand sticking out. And the red arrow is pointing straight ahead.
Isn't it going the opposite direction of where we're sticking out? Because if the car's accelerating, then we're going the other?
Not necessarily. It's the acceleration is the pull. I mean, it's not exactly, this isn't the exact acceleration, right? Because the exact acceleration may not be perpendicular.
Kind of seems like the arrow's pointing downwards.
Yeah, it is right now at this point. But then as you move along, it changes. So as you go down, the acceleration is going to kind of start pointing upward a little bit. So it's kind of bringing you, still trying to bring you within the center.
Some guys will have a sudden effect.
Yeah, but we're looking at these as unit vectors. So let's throw in the binormal. Now the binormal, you can think about the binormal vector as your head, your upright body. So that's the blue vector. So you're kind of starting off sideways.
Yeah, that's why I was confused, because it seems like.
And then you're doing some twisting. As you go down, you're kind of going the other way, sideways. And then as you go up, you're going sideways inward. Okay. Now, along with these vectors, there's also the planes that are important to discuss. And the first plane that we'll talk about is called TNB. Uh-oh. Did it freeze? TNP, yeah. So the first plane we'll take a look at is like the floor of the roller coaster that you're sitting on. So that's the plane that contains the normal, the tangent and the normal. And that is called the osculating plane. That's the plane that has the velocity and acceleration vectors. And then you have another plane TBP. The osculating plane contains T and N. If you're looking at the T is the X and then the other one is the Y. So NB. Is that the one? Is that the next one I want? BT. the second plane. The second plane I wanted to introduce is, shoot, it's not BT, it's NB. Had it right. The second plane would be like the back of your seat on the roller coaster. Would be perpendicular to the tangent vector. So the tangent vector will be like the normal vector for this plane. And then the last plane is just that third plane, ET. So that last plane makes that three-dimensional plane or three-dimensional space as you're moving around. So I think this is a little bit more complicated now because it has three vectors and three planes. But as you're following through, think about those planes as, you know, the side door of your, the floor of your roller coaster, the back seat of your roller coaster, and then the side door of your roller coaster. The osculating plane, the normal plane is the one that's perpendicular to the velocity vector, to the tangent vector. And then the third plane, I don't know what they call it. All right, so doing this by hand is extremely difficult except for one very special three-dimensional curve, and that is the helix. So the helix has cosine and sine, and it has a third component that's neither a cosine nor a sine. And so the cosine and sine, when you take the derivatives and you square it, they'll end up being sine squared plus cosine squared, which will end up being just a number. So a square root of a number, you can always take that out of an integral or derivative computation. So what I want you to do is I want you to work in groups and try to find the TNB for helices, and so I'm going to put you in groups.